Hello friends, in this video we're going to discuss about plane progressive simple harmonic wave, okay, that is traveling along x-axis. Suppose we have considered a wave, this is traveling along x-axis with velocity v, right, and it is starting from origin O. Let me consider that way, and we're going to obtain the equation for this wave, right? So before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you see the hype option, then please do hype the video so that I get better reach. Okay, so now let's start. Here you see, so we have considered a plane progressive simple harmonic wave starting from origin O. Let me write that. Suppose a plane progressive wave, simple harmonic wave, okay, is traveling along x-axis, right, with velocity v, starting from origin O, is traveling with a velocity v along the positive x-axis. Okay, we have considered that way, right, as shown in this figure. You see, now you see, let us consider a point at this position at x and at an instant t, okay. So displacement of this point is suppose small letter y, then its displacement will be given by y is equal to a sine omega t minus phi, right. If the initial phase is 0, then it's supposed to be sine omega t. So I have already derived in the first lecture description. In the description box I have given the link, so please watch that video first. Okay, now you see here, so what I'm doing, first consider a particle at this origin O. Okay, so wave is traveling in this direction, in positive direction, and wave is starting from this origin. Okay, it started moving from this origin. Now you see, at the time of starting this wave, start producing this wave. So when this particle will as the origin of the wave is this point, that means we have considered that wave is started traveling from this point O. When this O, particle at O, and let me consider another particle at x, okay, at position x, so it will start oscillate first. Okay, this particle at O will start oscillating earlier than this particle, because wave is traveling in this direction, right. So now you see, if we consider this particle, it initially at O, then its displacement will be given by y is equal to s sine omega t. Here phase is now initial phase is 0. So now you see, when this particle will be somewhere at this position, when it will go up, okay, then it will start oscillating, right, because it is this particle at O already started. Okay, after an instant it will start vibrating. Okay, so this will lag behind this particle at O. So let me take this as P, this particle is P. This particle, now you see, this particle P started oscillating later. Okay, but this particle at O started oscillating earlier than the particle at P. Okay, so that's why there will be a lack of phase, right? There must be a phase difference that we have considered phi here, and as this particle at O started earlier, so and this particle at P started later, so that's why this is lagging behind. So that's why I have considered for this particle the equation is y is equal to s sin omega t minus phi, right? Hope you have understood this. And for this particle at origin O, I have considered this equation, right? So hope you have understood this. Now let me write it clearly. Okay, so the displacement of the particle at O, let me use another ink here, particle at O at any instant t can be written as given as or given by y is equal to let me write a small y to represent this displacement at x is equal to 0. At this position x is equal to 0, right? So that's why I'm writing y 0 comma at instant t, so that's why 0 comma t is equal to a sine omega t, right? A sine omega t. So here omega is the angular frequency. Omega is the angular frequency of the simple harmonic wave, right? Simple harmonic wave. Okay, let me write it properly. So now you see, let me consider that the particle at this point is supposed P. This particle I am talking about, this particle you can see at x comma t. Okay, so here you see the particle at P start vibrating about its mean position later than the particle at origin O, right? At the origin O. So let us consider phi be the phase leg of a particle at P, okay, with respect to the particle at O. Then the displacement of this particle at P, let me copy the diagram and let me take a new slide. Okay, let me take a new slide. So here you see, so this particle at P lags behind the particle at O by a phase of phi, then its equation will be given by this equation, right? Displacement of this particle, then the displacement of the particle, displacement of the particle at the point P at any instant T is given by y of x comma t is equal to a sine omega t minus phi, right? So let me take this is equation number 1. Let me consider this is equation number 1, right? Now let me give you a situation. Here you see, suppose let us consider a particle is in uniform circular motion. Let me consider this, okay, and let me consider a simple harmonic wave here. Okay, now the particle at this position when t is equal to 0, suppose, okay, this will represent, let me take a number 1. If we represent this simple harmonic wave, if we compare this simple harmonic wave with this uniform circular motion, then you see we can take particle at this position starting from this position. Okay, if we compare this with let me take this as y-axis. Okay, this is x, here this is x. You can compare this point with this point, corresponding point. Okay, similarly when the particle at this position, let me mark it 2. Let me compare this one with this position, right? Similarly when this particle executing simple harmonic motion and which is in uniform circular motion, when it is at this position, let me mark it 3, then we can compare this particle with this position. Let me mark it 3. So similarly when it will be at this position, let me mark it 4, then we can compare this point with this. Okay, so when this particle will complete this one cycle, when it will reach the point from where it had started, then we can compare this position with this. Let me make it 5. So then we can compare this 5th position with this position, right? So that means we can say that when the wave travels a distance equal to its wavelength, that is lambda, and you know the wavelength of this wave is this, consists of a trough and crest, right? Hope you know these basic things. So then you see from this position to that position, length is lambda, and the angle subtended by this point completing one cycle at the origin is 2 pi. That angle will be 2 pi, and after completing this 2 pi angle, the wave starting from this position 1 to 5, it travels a distance equal to its wavelength, right? That means you see we can say that the phase difference between these two particles, between these two particles is equal to 2 pi, right? Hope you have understood this. So for a distance x equal to lambda, the phase difference is 2 pi, right? We can consider that way, right? So you see, for a distance is for a distance equal to lambda, that is wavelength change in phase is 2 pi. Change in phase is 2 pi, right? So therefore this particle, what will be the phase difference between these two particles at P and O? Now here you see distance between these two particles is x. So let me show you something. So distance between these two particles is x, this distance is x, right? So when the distance is equal to lambda, phase difference is 2 pi. So when the distance between the points will be 1 unit, then the phase difference will be 2 pi by lambda. And when the phase when the distance will be x, then 2 pi x by lambda, right? So hope you have understood this. So we can say that, okay, for a distance equal to x, the phase or the change in phase will be 2 pi by lambda, okay, into x, 2 pi by lambda into x. Because as I have already told you, when the distance is lambda, then phase change is 2 pi. When it is 1 unit, then 2 pi by lambda. When this is x, if you multiply x on both sides, then you will get 2 pi by lambda into x, right? Hope you have understood this. So that is the phase difference. Then equation number 1 implies y is equal to y of x comma t. That means y is the displacement of the particle at x at instant t, right? That is the meaning of y of x comma t, right? A sine omega t minus phi is nothing but now 2 pi x divided by lambda, okay? So omega is angular frequency. Means what do you mean by angular frequency? Again, if you compare this wave with this circular motion, right, when it completes one cycle, that is 2 pi, then if you consider time period t, then 2 pi by t is the angular frequency, omega, right? So here that will be that will be this 2 pi will be equal to this this part, that is lambda, right? Hope you have understood this. 2 pi is the corresponding phase difference between these 2 points, when the distance between the points is equal to lambda, right? Hope you have understood this. So now we have got this equation. So let it be equation number 2. And before that, let me do one more thing. Let me write here what is A. Let me mention that is amplitude. I hope you know the meaning of amplitude. I don't think I need to explain these things, okay? is the amplitude is the maximum displacement of a particle from its mean position, right? That is the amplitude. Okay, so and omega, the angular frequency is this omega is equal to 2 pi by t, where t is the time period. Time period. That means time taken by the wave to travel a distance equal to its wavelength, right? That is the time period. Hope you have understood this. So then this equation can be written here, you see, this way. We can replace this omega by 2 pi by capital T. 2 pi by capital T, right? We can write that way. Hope you have understood this. Okay, so now let me copy this last step. Let me copy this last step and let me take a new slide. Okay, so here is the last step. Okay, so from here what we're gonna do, so we're gonna take the 2 pi by lambda common. Let me take 2 pi by lambda common. So then what we're gonna have, y of x comma t. So just give me a second. Y of x comma t, a sine of if we take 2 pi by lambda common, then what we're gonna have within bracket. So here we don't have any lambda, so that's why we have to consider lambda by lambda here. Okay, on taking lambda common, 2 pi by lambda common, so we left with lambda by capital T into small t, or you can say lambda small t in by capital T. Sorry, let me write it properly. Okay, minus x, right? Minus x. That's what we're gonna have, right? So hope you have understood this. Okay, let me now you see here one thing, this lambda by t, this is the wave. It is traveling with velocity, and we know that time period is the time taken by the wave to cover a distance equal to wavelength, or you can say displacement equal to wavelength. So displacement by the time, that gives this velocity. So we can replace this term by v as well. So therefore we can write y is equal to x comma t is equal to a sine 2 pi by lambda into v into t minus x. We can write this way, since v is equal to, we can say v is equal to lambda by t, velocity of the wave, right? So hope you have understood this. So now you see this wave, we had considered initially that this wave is traveling along positive x-axis, positive x direction. If we consider that wave traveling along negative x direction, then instead of this negative sign we're going to put positive, right? So since we have already considered here, you see, before we derive this equation, we have already mentioned here that this wave is traveling along, let me go back to the previous first slide. Here you see this traveling with a velocity v along the positive x-axis, this is positive, okay, positive x-axis. So this equation is derived considering that this wave is traveling along x-axis. So therefore the equation of the wave traveling along negative x-axis, this is a positive direction. If you consider this direction negative direction, then we have to replace this by plus x, right? Hope you have understood this. So now here we're going to write this. Sorry, here it should not be equal sign. Okay, y of x comma t, y of x comma t, right? Now you see this equation, this is you can see this is the equation, this is the equation of a plane progressive simple harmonic wave traveling in positive x direction, or positive x-axis, right? So we can consider that if the wave is traveling in negative x-axis, negative x direction, okay, so if the wave is traveling in negative x direction, then the equation will be y of x comma t is equal to s sine 2 pi by lambda omega t, sorry, not omega t, v into t plus x, then it will be replaced by plus x, then this one will be the equation, right? Hope you have understood this. So that means in general we can write equation of plane progressive wave combining these two equations in this way: y is equal to s sine 2 pi by lambda v into t plus minus x, right? Plus minus x, right? Hope you have understood this. So let me go to let me take a new slide. So now you see what we can do. Therefore the equation of a plane progressive simple harmonic wave, okay, plane progressive simple harmonic wave is given by this. So here it should be plus minus x. For positive x-axis, here we're gonna put minus, and for negative for the motion along negative x-axis we're gonna put plus here, okay? So now you see one more thing. Now here we have considered the wave is originated from O, and when t is equal to 0, at time 0, this position, this particle was at origin. Now if there is an initial phase, that means at t is equal to 0, this point is not here. Suppose this point is here, this is the origin, and this point is somewhere at this position. Suppose this is the wave, then there must be a phase, okay, initial phase like this. If you compare it with circular motion, uniform circular motion, then it corresponds to this point. Suppose, okay, there must be an initial phase, let it be suppose phi naught, okay. Then this equation will be, if you say if phi naught is the initial phase of the wave, then the above equation will be of this form, okay, s sine 2 pi by lambda is v into t plus minus x, and here we're gonna have phi naught for the initial phase, right? That will be the form the equation, right? Hope you have understood this. Now you see what we can do. One more thing, it can be written in this form as well. So let me take this part. So here you see, if we consider this part, it can be written in this way, that if we multiply, if we open the bracket, then we're gonna get this, right, plus minus 2 pi x by lambda. Okay, we get this. Now you see, as you know, v is equal to lambda by t, v is equal to lambda by t. So here again this lambda gone, then this equation will be of this form, pi by t into small t plus minus 2 pi by lambda x. We used to consider this is equal to k, that is propagation constant. This term is called propagation constant. Okay, so and this is nothing but omega t, right, omega t. So in terms of, so that's why we can write this equation in terms of you know, angular frequency and propagation constant. Okay, so in terms of, we can write in terms of omega t, which is equal to 2 pi by t, and propagation constant k is equal to 2 pi by lambda. Let me clean this part. Okay. This is nothing but propagation constant. Propagation constant. The above equation y of x comma t will be given by a sine 2 sorry, not this time not 2 pi, this time we're going to write so here you see, let me show you again. So this part, I'm talking about this part here you see. So if we multiply 2 pi lambda v into t plus minus 2 pi by lambda x, so here v is replaced by lambda by t, and it gonna give us 2 pi by t into small t plus minus 2 pi by lambda into x, and this part is nothing but omega, and this part is nothing but the propagation constant kx. So we can write this equation in terms of angular frequency omega and propagation constant kx. Okay, so then the above equation of plane progressive wave, simple harmonic wave, will be given by this, right, plus phi naught. This will be the final equation in terms of angular frequency and propagation constant. So hope you have understood this. So we can write this equation in this way as well. So let me write it simply this way. Sorry. Okay, so this is the equation. This it can be written in this way as well. Okay, so hope you have understood this. In the next video, we're gonna discuss about relation between particle velocity and wave velocity. So stay connected. Do subscribe the channel if you are new to my channel, and please do hype the video if you get the option to hype it. Okay.